comparison tests is in the plural because there are two that we'll be looking at today. Some of you might even recognize these a little bit, the names of these at least, from some of your pre-calculus experience. So we'll start by thinking about 1 over x to the p, and I've given you verbatim what I'm putting up here right there, just because I want you to focus not on as much on writing as understanding, asking questions, annotating, making sure you understand why this works the way it does. So we've just discovered on the warm-up that 1 over x squared, when we integrate that from 1 to infinity, it converges. So maybe we can generalize that, not just for 1 over x to the 2, but 1 over x to the whatever. So let's go there. So if we have 1 over x to the p on your note sheet, you can follow along here too. But look, so you should really spend just a moment in silent study of what I've written here. Do you agree that this is the antiderivative? In general? Yeah. Keep in mind we're integrating with respect to x. P is a constant. So this is just the power rule. Do you agree that if you plug in b and a for x that you get this? The denominator on both of these is just going to be, this is, remember, negative p plus 1 just kind of comes along for the ride. So that's a constant down below that's just hanging out down there. B and a are the things we're plugging in for x and subtracting. Yeah. And now comes the big moment from yesterday. Now we have to evaluate the limit as b goes to infinity. So now this is an important moment because p, this in some ways, this limit depends on p now as well. So all this is a constant. So the thing we're focused on here is the blue part I've highlighted. Unfortunately, you can use your highlighter or something if you like. But I just want to make sure you're clear here. The only thing that really we're contending for is this blue thing, right? Like that's really the only thing in question. Everything else doesn't have a b in it. So we just have this is the question mark. What is the limit as b goes to infinity of this blue thing? Well, keep in mind that that's just the limit of this. Rules of exponents, yes? This expression is this expression. Do you agree? Okay. Just want to make sure everyone's okay with rules of exponents. So when does this converge is the question. Well, I think it's clear that this converges if p is greater than 1. Do you see that? Let's try a few values just to see that that's feeling right. We have, for example, b over b squared, if p is 2, say. Then we get, really, b over b squared, that's 1 over b, isn't it? Well, that converges to 0. Certainly if we did b the third or anything else, that works. Even b, though, let's roll back a little bit. Even b to the 1.1 would work, wouldn't it? Because you'd have 1 over b to the 0.1. So that would work. As b goes out to infinity, we would get, as b goes to infinity, that would go to 0. So that would converge. So as long as b is something, as long as p is something greater than 1, this will converge. If p is less than 1, then the opposite is true, right? Like say you have b equals, negative 1, say. Well, then what is this in here? B squared. Of course that doesn't converge as b grows large. Even if b is 0.5 though, even if p is 0.5 though, what do we have here? B to the first over b to the 0.5 is b to the 0.5. Well, even that diverges, doesn't it? So this is, I think, have we said this right? I think we have. Just want to make sure you're clear on why this makes sense. And then, of course, what about of course, you're dying to know, what about p equals 1? What happens in that case? Well, of course, then we have a 1 here. It's b to the first over b to the first. But if we're in the 1 case, keep in mind that that's always been an issue. X to the negative first, that diverges as well, right? And we did that case yesterday, but I'll put it here again, right? So if b happens to be 1, we get this special case where we have the natural log, and we can see that that diverges. So in summary, going all the way back to the original question here, let's just nail every single one of these down once and for all. You have the integral from some constant a, some positive constant a, to infinity of 1 over x to the p. That converges if p is greater than 1 and diverges otherwise. Okay, so we can finally say that. Do you see that we've not just observed that, but proven it? This is our proof here. We can actually work it out. Once and for all, we've proved that's the case. So if someone just asks you in the future, like, what do you think of 1 over x to the 5.6? You can say that converges. If all they're asking is, does it converge or not? You can say, yeah, I worked this out once and for all a while ago, and I know that converges. Don't make me do it again. The other results on this, and again, you have these here. So this is the one we just did. Yeah, I just copied it again here. But the other results can be established in almost identical ways. Like I could present the same page of mathematics that we just did again. It would be very, very similar. So I don't think it's worth going through. But take the time to focus on this second one and figure out why this is even an improper integral, first of all. Why is this an improper integral? There's no infinity there. What's going on? Okay, yeah, but we got the vertical asymptote case. So we have kind of the same situation. In fact, actually, you could establish this one the way we just did, or you could establish this through an argument about inverses. In some ways, that this is like these functions, the inverses of these functions are these functions. Doesn't it feel basically the same as if you reorient your coordinate system to integrate out to infinity along kind of a horizontal asymptote, as it does to integrate near a vertical asymptote going up? You just kind of like rotate your coordinate system and think about the inverse function. So you get the exact cases, the other cases, right, for that situation. And then this one's not hard to show either, but we'll omit the proof right now. Trying to get this comes up. Your homework makes you prove it or something, I don't know. But it'll be just a fun little exercise maybe for your chemistry class later today or something, for physics or something. You could be working on this. Okay. Off to the side in the English class. Prove that in general, for any c less than 0, e to the negative 2x, for example, something like that. That'll converge. Kind of makes sense intuitively too. You kind of understand that exponential functions hit that x-axis much faster even than the rational functions did. So you could probably guess that that's happening. But you can prove it too. All right, so let's actually say how we can use these facts in a more general way as we consider other integrals as well. We haven't yet come to any comparison tests today. So let's consider this integral, which I think, after thinking, together about the fact that 1 over x to the 5th converges, which we've all just established. I think we have a hunch that this one maybe converges too. Let's just stop also though and appreciate the fact that this is an integral that we really haven't equipped you to do by hand, right? Like, how would you have done this yesterday? As simple as this looks, could we have done this yesterday? Unfortunately, there's not a really nice antiderivative of this off the top of our heads, at least. And yet, we'd still like to be able to say that this maybe converges. We have a hunch that it does. So let's supply ourselves with some equipment to do this. So we've got this integral, certainly, that we've already shown converges. Can we come up with, besides just saying, they kind of feel the same? Well, yeah. So how can we formally compare these? So on your paper I have this too, and I didn't include the picture so you can draw this. But here's a picture of 1 over x to the 5th. Can you convince yourself that 1 over x to the 5th plus 1 is always less than 1 over x to the 5th? Why is that the case? Someone give a one-breath argument. Yeah. Yeah, for value, if x is always greater than 1, which is what we're talking about here, then this denominator is always greater, which makes the fraction smaller. I think that's a good argument. So I have in red and in blue all these things so you can see. Right here we get this. Visually, algebraically, this is definitely bigger. Visually, we can see that it's bigger. So if someone is saying, hey, we already established a few minutes ago that the area under this red curve, as we go all the way up to the infinity, converges to some finite number. Well, then the blue one clearly has less area than that under it, doesn't it? If you're less than something finite, then you are finite too, right? That's also deeply philosophical. Okay. So that's our first comparison test. So we'll put it in a box now. So this is how I would expect you to actually write out what we just said when you answer the questions on something like tonight's homework. Okay. You're gonna actually write out. I want you to kind of write this out word for word. Not word for word, but you need to have all these elements at least, right? Use tight, correct mathematical language. This is AP's demand as well for the level of communication that we expect. Do you see the elements of what we've said all captured in this sentence? Take a look at it. We'll come back to this box in a second, but what we've said is, since this converges, and this is greater than or equal to this for all x greater than or equal to 1, then it must be true that this also converges by the direct comparison test. And actually, I might add one more demand in here. I might put, since p equals 5 is greater than 1, we should maybe just say that that converges by the p test, the 1 over x to the p test that we looked at a second ago. So we can make a conclusion about the convergence of the integral, even though, notice that we haven't actually said what the value of the integral from 1 to infinity of 1 over x to the fifth plus 1 is. But we do know that whatever it is, it converges. All right, now let's look at the box too and make sure that this says what we want it to say. There are two elements of what this says. The first line should feel very familiar because that's what we've just done, right? If this converges, these both converge. If up here the hypothesis is met, if f is always less than or equal to g, right? That's the picture we were just looking at. There's the second part to this that we didn't really emphasize yet, and that's of course that if you have a series, an integral that you know diverges, then and you come to me with another series, it's always greater than another integral. Sorry, where are you? Use the language series here. And you come to me with another integral, then the integrand is always greater than my integrand. And mine diverges, well then so does yours, right? So that's what this is saying, right? If you're always greater than a divergent integral, then your integral diverges too. That's all. Okay. Okay. Well, let's try. See if we can convince ourselves of these. Let me give you just a minute to think about them. And then we'll try to write these up, not just kind of come to a conclusion, but also be able to write it using this kind of sentence that I've been modeling for you here, using the formal language. You can also just establish that this is not an integral we actually want to do. Would you agree? An important step in this process, I think, that we haven't really emphasized at all is identifying to what you want to compare it. Yes. Anyone have a hunch as to what you'd like to compare this to? What do you think? 1 over t squared. I don't see. Can you help us see that? Because it's not obvious on this. I should have started with an easier one, maybe. Sorry. But I think that's a good choice. Why'd you say that? Yeah, so I think this does feel mathematically, hopefully, at the place after having years of pre-calculus knowledge, that you kind of do have this feeling like so be there. this kind of has like the feel of 1 over t squared as we head out far toward infinity. So yeah, I think that's the intuition that we want to formalize as we write this. We want to maybe compare this to the integral from 1 to infinity of 1 over t squared dt, which converges, yes? 1 over t squared, that converges. So I think we want to show that this one converges. In order to do that, we need to show that the integrand here is always, what did we say before? Is always what in relationship to 1 over t squared? Less than that. So let's just try and argue that that's true, and we can just say it's true. But let's also just try to convince ourselves one with another here that this is in fact always less than 1 over t squared. Can we convince ourselves of that? I'm going to write this little bit off to the side here, and then this is what we want to show. To show that, we could show that t to the 4th is always less than t to the 4th plus 2t plus cosine t. Yeah? Is that obvious? Maybe that's already obvious, right? Isn't 2t plus cosine t, if t is greater than 1, if t is greater than 1, isn't this always positive? So I don't think we need to include this in our final argument, maybe, but I just want to like convince us off to the side here that we are right. And notice that I kind of worked from the conclusion backwards, but let's make sure it works forward, right? So since t is greater than 1, this is true. And since this is true, this is true. I just added t to the 4th to both sides of this inequality. And since that's true, if I divide both sides by this and divide both sides by t squared, I get this inequality, which is the one that we desire. I don't know, that would be a little side argument at least. Right? You could say that this is t squared over t to the 4th. T squared over t to the 4th. Well, this denominator is always bigger, using kind of Laura's argument from before. Right? T squared over here over t to the 4th. Well, this denominator is always bigger than t to the 4th. I don't know. Are we at least convinced ourselves back and forth, man to man here? Are we feeling good about that? Okay, so let's write it out. Okay, so since the integral from 1 to infinity of 1 over t squared dt converges because p equals 2, which is greater than 1. And 1 over t squared is always greater than our integral, t squared, our integrand, t to the 4th plus, what's a t? 2t plus cosine t. Since, I want to make sure my grammar is right, since this converges and this is true, can I say then? Does that grammatically work? Since this is true, then yeah, maybe I'll say. Write English sentences too if you want, whatever, however you want. It must also be true that the integral from 1 over infinity, 1 to infinity of all this converges to, and will permit you, at least you might on the AP test say direct comparison test, will permit you to say DTD. We'll know what that means. All right. Well, actually, in some ways, I said we should maybe open with this one here. This is a little bit easier, maybe, but easier in what way? I don't know. We haven't encountered one quite like this. Maybe. Do you have a hunch on this one yet? Yeah.
So it's kind of like 1 over root y, which diverges because p is less than 1. And because it's minus 1 is denominator, but it's greater, so it must also diverge.
Yeah, let's just write it up. Did anyone want Gabriel to say it again? If I were to say it, I wouldn't say it even a modicum of difference with what you just said. If you wanted to say it again, you can. But yeah, I thought that was well said. Okay, so here we go. So since the integral from 4 to infinity of 1 over root y dy diverges because p is 1/2, which is less than or equal. Which is less than or equal to 1. That's the test we established earlier. And 1 over root y is always less than 1 over root y minus 1. Or y greater than or equal to 1. It must be true that our integral diverges to by dct. Something like that. We have a function that is always greater than another function whose integral diverges. So our integral must diverge too. One other small, non-calculus question. Why are we integrating starting at 4? First of all, all this results hold, whether it's 4 or 5 or 6 or anything, right? You could make that constant be something there. But those of us who crafted this problem, why did we make it 4? Why couldn't we make it 2, say? Well, actually, 2 would be okay. Why couldn't we make it 1? I mean, we could have done 1 up here, right? But yeah, it would be undefined down there, so we chose 1. The other thing we didn't really stop to say, but maybe Gabriel and me and other people assumed that this would be obvious. Is this clear why this inequality holds? That this is actually always greater than 1 over root y? Yeah, we'll go with the Laura argument. This denominator is always bigger than this denominator. So this is a smaller fraction. You can say it that way again. What about this one? What's your hunch on this one? What do you think? Lots of you are already thinking, okay, well, 1 over x is a good thing to compare it to. Yeah, that seems obvious. What does 1 over x do? Diverges. This is that very edge case. Make sure you know the integral of 1 over x diverges. That's very easy to prove again. Natural law of divergence. Good. That's a good hunch. I think that's a very good assumption. However, what's the problem when we go to try to do the comparison test on this? You would be very happy if this was 1 over x minus 1. You'd be like, yes, apply test verbatim as we've been doing. But the problem is something goes wrong here a little bit with this one, even though we all have a very strong intuition, correct intuition, that this does diverge. So we now have to introduce another kind of comparison test, maybe to bring slightly more strength to our lives in terms of being able to make a conclusion about this. So I've just written what the problem is that Shivani highlighted down up here, right? We really feel like this diverges, but the direct comparison test we've just been doing, at least if we use 1 over x, this doesn't seem to work. Well, one way around this would be to compare it with 1 over 2x, I guess. So I'll write that out. I'll show you that that's certainly one way you could do this. So I'll just show you that. But I have another way of doing it too in a minute. But I just want to make sure you understand that this is actually perfectly fine and mathematically logical. I didn't write this on your paper, so if you want to write in bold what I have, you can. Read and understand. And use that and just process that. This inequality does hold for all the values we're looking at. Over here, you see what we've done? Certainly, an integral times a constant. If it converges, it still converges. If it diverges, it still diverges, even if it's an integral times a constant. So that's all I've done here. So that's one tricky way out of this, and you're absolutely welcome to do that too. That's very, just wanted to highlight that. But this is not the last sticky situation that we'll be in, and this little algebraic trick will not always help us or be there for us or work. So let's now turn our attention to something called the limit comparison test. Anyone still needs it? I feel like I didn't say all the things that are up here on your sheet, so let me know if you want me to say more. Do you understand the logic in bold too? If you want to use that logic. So limit comparison test is our way of formally saying that these still have the same limiting behavior. As we go out, we really want to say that 1 over x and 1 over x plus 1, for example, act the same way. Whatever one does, the other will do. If one diverges, the other must diverge. If one converges, then the other is probably going to converge too, right? This is our feeling, and this is exactly what is supporting that. This doesn't seem like very much to say, but this is actually saying quite a bit in these boxes here. So let's see if we can unpack this. And again, some of you who might at least took up my pre-calculus did something similar last year. We did learn something called the limit comparison test. Now I know that's a little muddy in our heads because that was in the context of series and not integral. So we'll come back to all these comparison tests in the coming days as they relate to series as well. I promise. This is why I keep sometimes slipping with the way I say these things, because we're going to do all these with series too. Okay, so let's think of f and g. This is the kind of the situation we were just in. We have an f, we have two functions, f and g. If we stack them on top of each other and then use our pre-calc knowledge to take this limit, which one wins out? Remember this whole discussion about rational functions? Which one? Evaluate that limit using all your pre-calc knowledge. The degree, comparison, right, all that. If that comes out to some number, then we'll basically say they act the same, right? If you stack two functions, and as you take the limit as it goes out to infinity, you get a number like 5. Well, then they act the same way. They're in proportion to one another. But what happens if you get 0? What does that tell you about this stack? As you go out to infinity, say this approaches 0. What is that telling you about the growth of which function is growing faster or something? Yeah. Okay, well that would be true. What can we say in general about the relative growth rate of f and g if this whole limit goes to 0? What can we say, Derek? I'm turning to you. What's up? Say? Gx. Yeah, g of x is growing faster. That's not super useful because the claim we want to make is that these are growing at the same rate, right? We want to compare two things that are the same rate. So that's not useful. That's why this inequality excludes 0, because that just showed that g goes faster. What happens if you get infinity as your answer? What does that indicate? F grows faster, right? So what we want to have them do is come out to some constant, which in a very informal way, you could say, indicates that they kind of tie, which is exactly what we want, right? A lot of times they'll come out to be 1 or something. And once we can establish that they tie, if we can find two functions that when we stack them, we get a limit of some constant that isn't 0 and isn't infinity, then we can make the conclusion finally that if one converges, so must the other, because they grow together. And if one diverges, so must the other. So that's a powerful claim. So now we can return to the previous example, and this time we'll approach it using the limit comparison test. And I'll show you how you might write that up. So we know that this diverges from see previous slides of this PowerPoint. Okay? We know that 1 over x diverges. You can even prove it quickly off this slide. And since, here we go, here's the limit. We're stacking these. It's a little messy, but since the limit as x goes to infinity of f over g, in our case that's 1 over x and 1 over x plus 1. Since that limit, work it out, is 1, and 1 is not 0, nor is it infinity, it must be true that this diverges also by the, this time we'll say by the limit comparison test. Again, I'm putting this in quotes here because this is the kind of thing we want to see right. Yeah? You like the limit comparison test? I want to make sure you have like a abiding understanding of this though too, like what we're actually trying to say here. Why we're avoiding 0 infinity. Why we can't make this conclusion unless we get a constant here like 1. A non-zero constant. In fact, you can even say that. You can say equals 1, which is a non-zero constant, therefore it must be true to our integral that diverges or converges. I'll put this up here. Let's see if we can do it. Maybe not. I'll write it over on the board. Maybe as we've done previously. I'll write this on the board, and we'll let me get RBC started, and then we'll have you take a crack at it right now though, right? See if you can say whether this converges or diverges, and explain why. I'll come back and put my version of my answer up in a minute.